you remember the first 15 minutes of class more than you remember the middle 30. So new information should come in the first 15. So let's do integrated first. You guys ready? Can you guys see this okay? Yes? Okay. In terms of work, because we're getting to the point where the units, the equations, some old units that we've talked about, gases and thermo, they all are going to start to build into kinetics and equilibrium. Everything needs to be labeled very well, because if not, I won't know what to talk about, nor will you. So when we're talking about integrated rate law, integrated means integrated with time, with respect to time. We have those 3 different versions of our integrated rate law, which relates to the different orders. An order is talking about the importance of a reactant to the rate of the reaction, right? So one reactant might be very important, so maybe first or second order. Or a reactant may have no role whatsoever in a rate, so it's 0 order. So in order to always respect that and write that, writing the rate law in the differential form would be, I think, pretty important to understand that it's first order. That's recognizing it's first order. Then writing down the integrated rate law as it should be written with your reactant given. Sometimes you can just put A in there, like A final, A initial. I just put the CV because that was like cyclobutane, I think, for that first example. And then pulling together the reorganizing the equation to solve for the unknown variable. Most of you guys did this. You guys put your K here, and then I think you plugged in there. I would just went a little further and plugged in by, what is this information here? Oh, sorry. I took the LNs together. If you have subtracted LN, you can now divide them. So that's initial minus final, so initial over final. You guys remember that law of logs, or law of natural logs? Okay. So then plugging in your information, 80 seconds, you get your units for K to be per second, so 3.60 times 10 to the -3 per second. Thumbs up if you got that right with all the work. Which of these do I actually need to go over? I know number 3. I know for sure number 3, but I at least want to let you see how the work should be set up. I don't do this for kicks and giggles, right? I'm showing the work because I want you to know the process and know how I expect you to set this up. Because if I start making suggestions and the suggestions are not taken up, I'm going to start making them requirements. You got me? And I might have to do that because it's just going to save you from yourself anyway. Because you guys like to not write down any work. And then part 2 is just basically was find the half-life. So the half-life equation for first order you've likely memorized, 0.639 or 0.693 divided by the rate law constant. So K, which you got in part A, 192.5 seconds. Thumbs up. This is for the integrated rate law. You guys good? Okay. Part, do I need to do number 2? I know number 3 was one of issue. You might need to refresh your memory, look back at your work, back at the question. I might use it as well. So 2 says it's second order, so I wrote down the fact that it was second order, so I raised the potassium iodide to the second power. That gives me the integrated rate law of the 1 over concentration final equals KT plus 1 over the initial concentration. So the half-life equation for the second order, do you guys have this memorized? 1 over concentration times K. Yeah, what's that?
You're going over the lecture problems. I thought we were supposed to do problems.
Oh, I am going over it's right here. I was like looking, you guys are giving me that weird look. I maybe pulled up the this is the problem set. Oh, here's the problem set. I just didn't scroll far enough down. I reset all my tabs when I opened it. Thanks, Lucas. Everybody else is giving me those weird looks, and I was like, am I doing earlier ones? Okay. Here's, let me start with number 3 before I move on. Can I start with number 3? This is the one that most people had an issue with. And I just even pulled out, my lecture notes. My lecture blog. Okay, so number 3. First order rate law, the constant's given to you. You start with your initial, integrated rate law, ln problem here. And then it tells you that your moles and your milliliters are given. We are never given moles and milliliters. We're always given molarity, right? Because we're talking about concentration's effect on the rate itself. So take your molarity, or your moles and your molarity to get, liters to get molarity. So we got 1 molar. Did we get 1 molar? Okay, I got like 1 thumb up, 1 head shake. So after you find that your K value is given to you, you have your time, because it says for 5 minutes. But you'll notice that your K is given to you in seconds, so you cannot plug 5 minutes into your time. You need to plug seconds into your time. So take your 5 minutes times 60 to get 300 seconds. And then your initial concentration is that concentration you just got. That is 3 sig fig, so it's 1.00 molar. And then ln of A is your unknown. So if you're solving for your final concentration, once you multiply, so well, I mean, I'm literally showing every step of the math, right? So once you multiply here and you have your ln over here of 1, that's 0. So then how do you offset ln? You offset natural log is e. So e to the ln of A final, ln's cancel out. E to the negative blah 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 is 2.32 times 10 to the negative 1, so 0.323 molar is your final concentration. So that's just your final concentration. The question states how many moles of dinitrogen pentoxide is left or remains. So if the question's in moles, how do you get from molarity back to moles? You have to implement the volume once again. So this is molarity times liters to give you moles, so 0.116 moles. So sometimes seeing the process is important, sometimes writing the process down, but at least give yourself a chance to kind of see that it does take a little math. Don't neglect the math. All right, so part B, how long will it take for the quantity to drop to 0.1 molar? So it's saying how long, it's asking for time, right? So once you solve for time, you'll have your answer. So I went ahead and rearranged my integrated rate law for first order to solve for time here. So if we're going from initial concentration, so our initial concentration, which was 0.1, my bad, 1 molar, which was given to us in part 1, and if it says we're dropping to 0.1 moles over the 500 milliliters, which is 0.5 liters, that's our final concentration we're looking for. And I did see a couple people plug the 0.1 in there instead of the molarity version. You guys plug moles in, so no moles, it's all concentrations, it's going to be all molarity. And then once you find your time, after you plug in your values, just solve, you get 330 seconds. But I think that setup was weird because you have moles given to you versus molarity. Alright, can I ask what other ones I should do 1 through 9 versus all of them? Yeah.
I should have a question on number 4. How do you know that it's 0 order?
So, it says 0 order.
Oh.
Because it says many reactions occurring on a solid surface are 0 order.
Oh.
An example being a thermal decomposition of nitrous oxide on a finely divided gold surface, blah, blah, blah. It actually says 0 order right there.
Oh, I think it was like cut off at the top.
Oh, my bad. Well, there you go. It's 0 order. It would tell it to you. You wouldn't have to assume. But many times your catalyzed reactions are the ones that are 0 order because the concentration increasing or decreasing won't affect the rate, but a catalyst will. So adding a catalyst a lot of times is going to be because it's a 0 order reaction. So when you do plug that in, when you actually know it, your concentration final is equal to negative KT plus concentration initial, and so that's that over there. I just modified it so I can have the negative over there. So in terms of plugging in rate law or rate constant given to you, the time given to you, the initial concentration given to you, you can solve for your final concentration with 0.60, 0.06, dyslexia. And then how about any more from 1 through 9? Most of us got the hang of it after, I think, those short ones anyway. You guys got those done quickly. How about ones that you didn't get right? Yeah, John. Number 9, thank you. So number 9 has the rate constant for second order, so it's telling you the second order. So here's your integrated rate law for second order. It's got the one with the positive slope here. It tells you the rate constant, so K is 0.4 or 0.54 per molar seconds. It tells you that the temperature is 300 centigrade, because whenever you have a rate established, a lot of times you have the temperature given to you as well. Is temperature involved in integrated rate law whatsoever? No. Little t is what? Time, right? So they sometimes just, as a standard, tell you the temperature as well, because if you have a higher temperature, what do you think is going to happen to your rate? It's going to increase, right? So they sometimes just tell you the temperature. Don't utilize it whatsoever. how long will it take for the concentration to decrease from blah to blah. So you have your initial and final, you have your values to plug in. I would just find your numerator first. So after you rearrange some solve for t, I would just take your 1 over the concentration final minus 1 over concentration initial, solve, and then plug in your 0.5 or your value up here, and then when you divide, you get 3.6 seconds. You just have to recognize it's second order. That's the only issue I think there. All right, so how is this different than the first rate laws we did? First rate laws, differential rate laws. Who can give me a little synopsis? Go for it, John. Or go for it, Binky.
This one has to do with like time. The other one, differentiated one, has to do with like rate.
Okay, so they'll give you rates, but how will they give you rates generally?
Like in the table.
Okay, so the table's got concentration and rates. This will, and a table could be what? If it were integrated through table versus through the information given out in the problem. What kind of, I guess if I wanted to integrate rate law, what kind of data would be given to me in the table?
Just time.
Time and
Concentration.
concentration. For your lab, what kind of tables do you have? What's in your data tables? Ignore the whole Beer's law line. That was a prep to actually be able to establish the law. What's in your tables?
Time and concentration.
Time and concentration. So have you guys done your R-squared values for each of the styles of integration?
Yeah.
Who has a pretty, who has a good R-squared value? What do you guys have, Alvin?
0.98.
For which integration?
Second order.
Okay, second order is 0.98. Who else? Who has something that they would call their conclusion? Let's go. Anybody? Yeah? Where? Zero order. 0.99. Okay. Anybody else?
There's really 0.99 for all.
Did you guys, I guess let me ask this first. The data you put in your table initially was from Lager Pro, right? That data was absorbance versus time. Did you take your absorbance to concentration? I might need to check some math. How many data points did we throw into our stat plot? 10. Did anybody try 20? I might, if you can't come to a conclusion because they're all linear, I might, well, let me back up. What data points did you plug? Very beginning or well spaced throughout? Well spaced. Did you go to the very end? No? Where did you stop? Where did you truncate your data?
We had 300 seconds of data, but stopped at like 180.
Is that where it started to fall very close to zero? Zero absorbance?
It wasn't really going down anymore.
Okay, or so it was stagnant.
Yeah.
I might suggest that if you're not coming to a conclusion, because everyone's conclusion looks like it's gonna be a little different. I'll tell you the actual order a little bit later. But I would choose maybe in the first 50 to a minute, so 50 to 60 seconds. I have one group that has a little bit of weird data, but 50 to 60 seconds, maybe, because that's going to be the initial rate where, maybe not the very first, because you guys didn't pop it in there until probably 5 seconds after you started data collection. Basically the first good 50 to 60 seconds. Let's see where that goes from our data collection if you can't come to an agreement with your data. So I'll have to look at y'all's your actual conversions. All right, I'm gonna switch modes. Let's go to graphical stuff real fast. Graphical. So without that, page 1 through 7 in your packet. Look with Courtney for me right now, because I unless for some reason it's in my other book bag. All right, let me make sure I'm pulling up the right information. Is this the worksheet, guys? We're on the right one. Okay. Sorry, I tried to pull them all up here with all my other stuff with Honors Chem. So I only saw a couple of those that you guys needed help with. The first part was just information guiding you through how do you look at a graph. You guys will have to show graphs for me, at least with the, I'm linear, I'm not linear, but by giving a sketch with the R-squared values across a couple of our problem sets we'll do later. And then here's the first one that you actually had to do. So first off, you looked at the graphs. These graphs were given to you, so it was second order because that was the only one that looked fairly linear, and it was the only one. So they gave you the 0.985 and then 0.999. So second order was the best fit. So you saw it was second order. Most of you guys did get to your slope by looking at, your K value by looking at your slope. The slope was given to you where on these graphs? In that, well, where's this? The The slope, you don't have to calculate your own slope, right? It's given to you in the y equals mx plus b format. So that would be your, nope, not that one. That would be your slope, 0.0142. But your job is to establish the correct units for this. If this is second order, the second order rate law, which is rate equals k concentration squared, you have to cancel one of the molarities out, so you have to have molar and then time. They did not, I called it seconds because they didn't give you a time unit, so I just put time. You could also put molarity per molarity second down there. And then for half-life, some of you guys, I might have a rough time with this. I have to re-derive my half-life equation if I forget, because I will look like, is this second order or is this a zero order one? So if you can memorize your half-life equation, 1 over k times the initial concentration, you can do that. Plug in your data here and then your initial concentration here, or sorry, your k value and then your initial concentration. But if you can't remember that, derive it yourself from the second order integrated rate law. What's another way to find half-life from the graphs given? Yeah.
Look at like where it's at the concentration.
So which graph would be appropriate for that? Because not all of them, right?
No, you gotta look at like the concentration versus time.
Okay, so I plugged into the half-life equation and got about 4,400 seconds. Who got it something close? Okay, that's exactly the same if you plugged into the half-life equation. If you look up here, which there was 2 or 3 years ago, there was a question that asked about half-life, and all they did was gave you a graph, and then you had to do some extra work with it. But my students were like, we totally blanked, we couldn't figure out how to find half-life. I was like, what? Are you serious? And so, because they didn't have a rate law, nor did they have concentrations initial necessarily, just had a graph. That graph was this. And so they had forgotten how to find half-life. So in this case, it's the time it takes for half the concentration to dissipate. So we're going from 0.016 to 0.08, right? So then you go over here and you drop down. It's a little rough. So it's about here. So that reads about what, 48 or so, 4,800. So what they do is they give you some wiggle room. If they see you're doing graphical analysis, they'll go with that basic range. But if you're doing half-life, it has to be spot on, because there is only one half-life equation for a second order. Okay? So you have some wiggle room, but make your choice which one you want to stick with. Okay, so that's our number 1. From number 2, this was the explanation-based one. I'm going to find I don't have my packet right in front of me. There it is. So, this is on page 9. So what are the methods, 3 different methods? So first off, to find the order, use the data table doing table logic. Look at the R-squared value if you go through integrations. Or, I think that's it. It says 3 methods. Here's your table data, 1 with R-squared values. That's for linear regression, doing your integrated rate laws. Using data from the table to calculate your own. You could calculate your own if you have concentration versus rate. So this is this is kind of the ugly algebra method as well, showing the rate comparisons with the concentration comparisons so they can find your order. The last one is doing instantaneous rate, which you won't often do, but you can take your graph, find a point, do your slope, your tangent at that point anyway. So once you find the slope of that line, this would be a concentration versus, I don't have this on here. Oh yeah, I do. Concentration versus time graph. So when you find the concentration versus time graph, it's likely going to be exponential decay, because as the reactant concentrations decline, the rate takes a longer time, so that's why it has that slope to it, that little decline. So when you take your instantaneous point at that particular time, you take your tangent there, you do your rise over run, you have a slope, that slope is your rate. You can take that at 2 different times and compare 2 different rates. So basically making your own data table from a graph. That's the point that maybe some people are a little iffy time on, but it's not that hard. Just have to make your own data table. So that was the 3rd method there. And then what are 2 different methods by which you could find the rate constant? What's one, Alvin? if you have the differential.
Yeah, right, and, right.
Okay, so from rate and concentration, find your own K, if you have that information. What's another way?
The slope of the integrated rate law.
So if you have the integrated rate law and you know the order, you can find the slope. That's pretty much it. You can also pull data from a graph and find your own rate at a specific concentration, and then find your K value. For half-life, two different methods. We kind of just went through this, but you could find the formula itself, plug in the time, plug in the rate constant, find the time, or you could pull it from a graph at the time it takes to get to half the concentration. Looking at the time it takes to get there. So it would have to be a concentration versus time graph. So you have to be very specific with your axes that you're speaking of when you do explain these. All right, do I need to go over the third page right now? Give me some help here. Some of you guys are with it, some of you are still not. This is helpful. Some people it is, okay. I'll just quickly go over number 3. So from your data, so the two methods that you could use to determine the rate law, you can either take the time, if you're ever given a time versus concentration graph like this, that has to be integrated rate law, right? Because time is not given for anything else. So that's going to be, what do you plug into your stat plot for integration? Time goes where? L1 or x-axis, okay, and then the first integration I always do is 0 because I just plug my concentrations in. So when you do your L1, L2, that'll be your time, and then your L2 will be your concentration. You do your ln reg, get your R squared. If it's 0.99, it's probably 0 order, but you do have to double check with all of them. That's how you justify your reasoning, just by showing all of the integrations. So then you natural log the concentrations, ln reg, and then you 1 over the concentrations in ln reg to figure out which plot is the best fit, meaning the best relationship, meaning the order. The other one is you can make a graph and then do instantaneous plot, tangent, find your rate. If you, for this one, we did have the data points given to us through graphs. So each of these graphs had their ln reg and then their R squared values given, which is very nice. So you can see that this was the most linear at 0.999. So it's definitely a first order reaction because that's the best relationship for this particular reaction. So when you write down your rate law, the actual rate law itself, not the integrated rate law, the actual rate law is the differential version. So K hydrogen peroxide to the first power. And then what's the easiest method to determine the K value? If you already have the integrated rate law, which we do have here, through graphs, you can find the slope of the ln concentration versus time because it's first order. Because slope is K in our integrated rate law, you can actually solve for it if you pick your integrated rate law and then you plug in values for your initial, your final, and your T value, which you can do, or you can do instantaneous yet again. I highly doubt anybody's going to do instantaneous. It takes a little bit more work. Anyway, I have time for that. And then once you do see that, you can pull your data. You see 0.0008 per second. So and you also should be able to find the constant or the value of the units for K very easily. So if it's first order, it only is by time because who's getting the rate of the molarity whenever you have your rate law? Rate's equal to K times concentration. K has to be the time, so per time, because this is molarity and rate's overall units are what? Molarity per time, right? Or molarity per second in this case. So K's units, I think, are achievable if you think about it for a second about how you get the appropriate units for rate itself. And then for half-life, do not use the integrated rate law graph that you selected because it is not the appropriate graph for half-life. The appropriate graph for half-life has to be concentration versus time. So that's the part I didn't highlight that day we did integrations. It has to be concentration versus time because that's the only one that has a clear, I know the concentration initial, I know the halfway point, so going from 1 to 0.5. I can go over to see the time it took to make that happen, which is about 850 seconds or so. So 850 seconds was an estimation based off the graphical analysis, or you could plug into the first order half-life equation to get the exact, so 866-ish. And most of the time they give you, I don't have a good estimate, most of the time they give you about a 50 plus or minus window of your range whenever you do your half-life, because it depends on how you do it yourself. Okay? All right, so I'm going to stop there for now. Do you have just overall questions right now on kinetics? It's hard to pull it out right now, but if you have an overall question about kinetics, let me know. Okay. Hold on to your horses. We're going to do mechanisms in about 20 minutes. Okay? Mechanisms is like the easiest part of kinetics. It's very nice. Who remembers Hess's law of summations? Okay. What do we have to do to get to the final reaction?
Rearrange everything.
Say again?
Rearrange everything.
Flip equations and stuff to get to the final. But what did you do with all the reactants and products to make the final? So that they cancel, right? We're not going to do any rearrangements. We're simply going to cancel, and that's it. So it's one step less, okay? But before we do that, you guys have your NSMI packets. You're reading, yeah. If you don't, pull out your outline maybe. I want to talk to you first about. I'll go over the more kinetics homework in a second. I didn't do that yet. Okay. In terms of vocabulary, you guys thought thermochemistry had a lot of vocabulary. You're definitely right. Thermochemistry has by far the most vocabulary of our entire Chem life. Kinetics is like second behind thermo. So I want to make sure that you're clear on when you're using the vocabulary, you know what you're saying, and you're using it correctly. Does anybody remember or look back? I think it's a little bit, maybe page 20 or so in the packet. What's an elementary step? Look on with a friend. Levi, you need a friend. Come sit over here with Sean. Sean does not bite, right?
What?
Only on Tuesdays? Alright, page 21. What is an elementary step? I think it's page 21. That's molecularity. It's on page 22, I lied. Page 22? Go for it, Courtney.
A reaction whose rate law can be written.
Okay, so the rate law can be, rate law from, I'm going to abbreviate this, from the balanced complete equation. And when you said molecularity, I thought balanced complete equation because molecularity is a term that does describe that. So, if you ever say the word molecularity, what you mean is the balanced complete equation numbers, aka the coefficients. Normally, if I give you a reaction, I'm like, tell me what the rate law is. Are you allowed to use the reaction itself to write the rate law? We've never done that, right? We use data tables, we use integration, we use graphs. We never, ever, ever, ever write the rate law from the reaction. But if it says it's the elementary step, it means it is a step that has no internal mechanism of like, oh, I look like one reaction, but I'm actually 4 steps. An elementary step is a step of an entire reaction. So, and I'll show you a graph first that maybe will explain what that means here. But many of our reactions are multi-step reactions. 2, 3, 4 steps that are happening in solution, but we don't see it, right? We don't even know it's happening. And so now we're really focusing on what's happening in the entire reaction through the steps it takes. So the steps look like this. You guys have seen an enthalpy diagram like this before, but we've only seen like one big hump, and we looked at the beginning and the end, which thermochemistry was all like state functions. We looked at the initial, we looked at the final. Who cared what happened in the middle? Now we're looking at the middle. We're looking at what happens in between. So the reactants react, they form an activated complex. The activated complex forms a product. Well, this product is not the product, right? The product is over here. So what do we call this in the middle? What's in the middle? Starts with an I. Give me an I. Give me an N. Intermediate. Okay, so we formed an intermediate because it's not the final, it's intermediate between the original reactants and the final products. So this intermediate gets reacted, the second step of the reaction makes a new activated complex, and then it makes the final products. How many steps are in this reaction? How many steps? Two steps, that's it. And in this case, you can see some information about activation energy, the energy of products, and energy of reactants, and similar. For a second, or for a second? Thanks, bye. Okay. So anyway, you can definitely see these are elementary steps because they're single step, but overall this is called two-step reaction. So what we're talking about is each of these individually, and if we have an elementary step, we can write the rate law for it. Okay, molecularity refers to coefficients from a balanced chemical equation. That term molecularity, make sure you're using it correctly. And then you guys tell me, this is on page, someplace right there, what are the 3 rules for verifying a reaction mechanism will be valid? It's on page 21, I believe. Talk in your groups for a moment on that, because I need to take attendance. Quickly. Anybody? 3 rules for verifying a reaction mechanism is possible. Thank you, Courtney.
Must be determined by experiment.
Okay, so everything we've done so far has been experimental, right? What else? Okay, so overall stoichiometry means the coefficients must match, which we'll talk about that in a second. Keep going. Okay, so the rate law from the experiment must match the elementary step that controls the rate of the experiment. So, what was the term we used to say, I'm the step that controls the rate of the experiment? We called it the slow step. It's the slowest step that controls the entire reaction. What's another name for that? Rate determining step. So the rate determining step, aka the slow step, is the elementary step that controls the rate of the experiment, or the rate law itself. It has 2 names, though, slow step or rate determining step. So we're going to talk about that here now. And you can see that it's very well labeled. For example, this is example 10, or example 10 in your packet. They give you the overall balanced chemical equation of our nitrogen dioxide and fluorine and so forth. Then they say the experimentally rate law is K, first order for nitrogen dioxide and then first order for fluorine gas. And then they say, here's the mechanism. We think. A lot of times the mechanisms, they're not so attainable because it's all happening in a mixture. You can't always isolate the intermediates. It's difficult to determine exactly what steps they're taking. So we make really good guesses at what we think the steps are. So they said the step 1 was nitrogen dioxide plus fluorine gas makes this guy and then a fluorine atom. And then they said second step is fluorine atom, which was produced over here, reacts with another NO2 to make this guy. So what we would do is then go, do these steps add up to the overall reaction? And they do, because all you have to do is think about Hess's law, and you're going to cancel things that are the same on opposite sides. What can cancel? The F atoms, right? So this F atom is made and then immediately consumed, right? It's made and immediately consumed. It's no longer there. What else can cancel? That's it, right? Okay, so then everything else comes down to the bottom. So we have an NO2 that stays. Oh, but there's 2 of them, right? So you put a 2 there. And then there's a fluorine gas, F2, that comes down. And then what here? 2 of these guys. All right, does this match this? Check. Okay, 1 criteria is met. The overall stoichiometry of the added up mechanism steps matches the reaction itself. Second determinant is what? Well, first it says it has to be experimentally determined. It says experimentally determined. We're good there. Okay, so that's 2 criteria met. What's the next one? The experimentally determined rate law must match the Who controls the reaction? The rate of the reaction. The slow step. Okay, so does the slow step's molecularity, which is 1 NO2 and 1 fluorine gas, does the slow step molecularity match the rate law? Yes, the coefficients are the orders. This is the only time where coefficients can be determined to be the orders, is if we're in the elementary step stage, which we are here, and we're looking at the rate law, that's the determining step, which is the RDS, rate determining step, which is the slow step, and it matches 1 and 1, check. If all three of those are met, it's experimentally determined, the slow step matches the rate law that's given, and the mechanism steps add up to the overall stoichiometry, those three criteria met, we call this a valid mechanism. The mechanism is a possible explanation for how this reaction actually occurs. Even though a lot of times we can't always figure it out, we have to propose steps that we think would be the steps that are happening in that gap where we don't always know what's happening. All right, so that's what a mechanism is. Let me elaborate now. Okay, who feels good about that so far? Thumbs up. Yeah, okay, let's do this a little bit more then. Let's look at some more vocabulary. So we just went over this. This is just a snip of your reading. You guys will have to do a little bit of reading for me on that one. And here's the vocabulary that I've mentioned that you might want to note in your packet. Star it, write the word down, take a picture, do what you got to do. But if we're talking about, this is where I want to show you. If we're talking about a mechanism, it is the sequence of bond making and bond breaking steps, meaning we have to have these reactants degrade and these products are made. So mechanism is a series of steps that's occurring through the entire conversion of reactants to products. We call them bond making and bond breaking because that's what's actually happening. So that's what a mechanism is. You can also just say it's a series of steps, and those steps are called elementary steps. So during the reaction, during each of those steps, we make products. Well, not all those products are the products that are at the final step. So those things that are made intermediately are called intermediates. Those intermediates are immediately made, are made and then immediately consumed. So they are not in the final rate law itself. So you'll see them as a product in an early step and then consumed immediately. So that's how you identify an intermediate from elementary steps given out to you in a series. We already explained kind of what the elementary step was. It's one single step of a mechanism which you could possibly write their order for straight off the bat from coefficients. Yeah?
So fluorine atom was the intermediate from the...
Yes, fluorine atom I think was the only intermediate in that last one. Yep. Rate determining step is the slow step, so we call it the RDS, rate determining step, and it has to match the rate itself because the rate itself reflects the overall mechanism where one step is the one step, the slowest, weakest link. Like on a relay team, the slowest, weakest link controls the overall time of the team itself. And then molecularity is just a term to describe coefficients or the balanced complete equation coefficients. It also can tell you how many, based off numbers, tells you how many reactants collide to make this reaction happen. So if I have one reactant, two reactants, or three reactants, I call these different things. It's called unimolecular, uni, 1, bimolecular, 2, bimolecular, and then can I get the last one? You want to say termolecular. And so that describes the number of collisions that would have to, the number of reactants in the collision for that to be an effective collision to force the reaction to occur. Question?
Can the elementary step and the rate determining step be separate? Like maybe 2 different steps?
So you can have, for example, you can have 1, 2, 3, 4, 5, 6, 7. You can have as many elementary steps you want. One of those elementary steps is the rate determining step. Does that make sense? Each of those is called an elementary step. Good point. I didn't describe that. Okay, so which of these do you think is a really difficult reaction to occur successfully?
Turn.
Why turn?
Because that's the molecules combined.
Same time, correct orientation, and enough energy. That's got to be like a perfect situation where you have three things colliding with the same, enough energy, correct orientation, and at the same time. It's a little easier to get a bimolecular reaction to occur, and what would be a good example of a unimolecular it has to just decompose. It just has to get rid of itself. It just splits in half or something like that. So uni's not as common as bi either. All right, so that's some vocabulary for you. We kind of just went through this. The other one is experimentally determined, but we said some of the elementary steps, rate law written from coefficients from the elementary step. The weakest link is the slow step, and then we just went over that too. So I'm doing some of this orally with you and some of it on paper, but a lot of it's just going to be let's practice this together. All right, so here's our mechanism given to us in 2 steps. The overall reaction is given at the top. The experimentally determined rate law is given in the middle. Tell me, tell me how I would determine if this is a valid mechanism for this overall reaction. Okay, so do the coefficient. So I guess tell me first, who, according to the rate law, is the rate determining step? Step 1 or step 2? So according to the rate law itself, that molecularity has to match one of these. Why step 1? Because there's 2 NO2s or 2 nitrogen dioxides, and there's 2 nitrogen dioxides there. So 1 and 1 makes 2, right? So the molecularity of this is 2, and according to the rate law, which is second order there, this seems as if it's the rate determining step because that matches the molecularity. Okay. Second question, are there any intermediates in this particular mechanism? NO3 is, right? Definitely, because we're producing it and then immediately consuming it, right? Anybody else? That's a remaining product at the end. It doesn't get canceled. Okay, what would you call this? A catalyst. Okay, so remember the definition of catalyst. Catalysts are things that are reactant. I'm not going to say reactants. They do not change over the course of a reaction. They do not get used up in the course of a reaction. They stay the same over the course of the reaction. Do you notice that one of these is left over here at the end? So I'm going to cancel one of those out. Just one, yeah. If I cancel just one of these out, you'll notice that one of them still remains. However, this is serving as a catalyst for itself. So the definition of catalyst is that it starts as a reactant in step 1 of our elementary step systems here, and then it ends as a product at the final step. But then at that point in time, in terms of simplification, we do have to cancel them out because they are not. One of them is not there. Yeah. It doesn't show up in the final reaction. It doesn't show up in the final product. I'm sorry, it doesn't show up in the final product. This is a weird example because one of these is serving as a reactant and one of them is serving as a catalyst. And so that might just be an energetic form of itself. Question?
Okay, so is the first step the rate determining step because the hydrogen dioxide's in the reactants, or is it because there's more nitrogen dioxide?
It's because the molecularity of this reactant set matches the rate law itself. Being bimolecular, so 2 of those, and then there's 2 of those. That's why this first step is the rate determining step. The second step is not. It's because of the matching nature of it. All right, let's do a second example similar to this, but we'll actually work through the whole thing out. So I showed you that these graphs can be a little different, right? They have 2 steps to them, or 3 steps, and so forth. Which of these, this one actually tells you, what you can see is that the rate determining step is the one that's the slower step. Well, how do you view that visually? The step that takes the longest is the slowest step. So who's going to take longer? One that has a high activation energy, or one that has a low activation energy? High activation energy would take longer to achieve, and so the longer to achieve step 1 is the rate determining step, and then there's a second assumption you can make about that. Each of these steps can have their own rates associated with them, and so each of these if it has a rate, it has a K value associated with them as well. So rate's equal to K times some sort of reactant to the X power. Well, rate itself is directly related to K, the rate constant. So if the rate is slow, the K is also low. right? So you also need to make this assumption whenever you find which one's the rate determining step, is that the K value is also smaller for that step. So you could say K1 versus K2, meaning the two separate steps it takes, and then you can make the secondary final comment that K1 is less than K2. So it's just one extra step of assumptions that you can make about your mechanism itself. All right, let's keep going through a couple more examples. So in this one, this is saying it's a suggested mechanism, so then you have to make sure the criteria fit to make it say it's a valid mechanism for this particular reaction. So you look first, I'm just going to look first and go, does the rate law match the slow step? And the slow step is identified, right? Does the rate law molecularity match the slow step molecularity? Yes, right? Because this is a 1 and a 1, this is a 1 and a 1. So 1, the molecularity step is met. So when you're describing these, you do have to say 2 sentences at least, right? Criteria 1 is met, molecularity of the rate law is first order, which matches the coefficients of 1 and 1. Second, you want to make sure that the overall mechanism matches the overall reaction. So sum these up. What can cancel? This is the same example, yeah. 2 F's and that's it, right? Okay, so then 2 of these come down. Oops, plus F2 yields. So I just took these down with me. And then this one and this one come down as well. So that's 2NO, 2F. And so which of these would have a lower K value? The slow step. And then check the mechanism, the overall mechanism matches the overall reaction. So no, this is an intermediate example. What is the intermediate here? And what's the catalyst here? Nitrogen dioxide is the intermediate, and nitrogen monoxide is the catalyst. So this is the catalyst because it's present in the beginning and then present at the end. Does not change over time over the course of the reaction. So catalyst is in red here, and then the intermediate is produced and then immediately consumed, right? So intermediate is in green. What is this overall reaction? Look and see what cancels, right? The stuff I've circled cancels, right? Because it's on both sides of the yield symbol. So all of this cancels. So what's the overall reaction? So ozone plus oxygen atom yields 2 oxygens. This is what happens in the upper atmosphere, the ozone layer, where you have free radicals of oxygen. The free radicals of oxygen attacks the ozone molecule, meaning ozone goes away, but it makes oxygen. Do we really want oxygen in the upper atmosphere? No, we want ozone in the upper atmosphere, right? We need that to shield us from the UV radiation. No one's up there breathing oxygen. So really, this would be great to happen at the lower atmospheric levels, but it doesn't necessarily occur. It does take a little energy to do. All right, last one I'll do. I have a couple more examples. I might save those examples. Let me see if you guys can get started. You guys have in your packet an example that looks like this. I'm going to do catalyst in a second. You have a sheet that looks like this. It says mechanism practice. So I want you guys to work in groups on that for maybe 15 or so minutes. Work on that first, and then I'll answer some more questions related to mechanisms. It's on page 15 in your packet. Page 15.
When you do chest corrections, when you do chest corrections,
You emailed it to me. I have no bad.
is that the, okay, so when I email it to you, is that unit 3 or is that unit 4? Unit 3 hours?
Yeah.
Okay. Yeah, I had my bag here.
No, I have that, and I was right here. I just wanted to figure it out.
Okay,
No, I
so
saw that yesterday. I totally just neglected.
okay, I just wondered because I saw this right here and I remember doing the
but I just need that in the box so I can give you full
Yeah,
credit.
which one is
Because
that?
I've missed somebody else.
Yeah, because I remember doing it, and I was looking at this, like, where did I write it down at? And I didn't remember.
Oh, guess I know. When are the thermal experiments due?
What do they do? I don't have a due date yet. It'll be probably right after your test for kinetics. So I want you guys to focus. Your test for kinetics.
On Monday?
What number are you guys on? We made it to 10. I know you're over 10 and 12. How about some others that you guys encountered? Yeah. 13. 10, 12, 13. Anything else? Right now? Okay. So I'm gonna have you guys just stop on them in the middle of that question. I did have a couple questions on the molecularity, and so this is a quick recap of that. If you have a single reactant, it doesn't matter what the reactants are. Single is uni. Two reactants is bi. 3 reactants is going to be very rare, but that's the term molecular one because it does have a simultaneous collision that must occur with activation energy and correct orientation. Remember, effective collisions are what we have to have in order for the reaction to occur. So effective collisions, the criteria whenever day 1 is the activation energy is met because it has to break the bonds, and the orientation must be correct for them to reorganize in the correct manner. But you can definitely see how these elementary steps are reflected. The molecularity of the elementary steps are reflected in the orders over here. And so those should seem very similar to you, especially if we're talking about reactants of elementary steps. Second, in terms of activation energy being adjusted as a catalyst is added, for this blue curve here, you have a single step is what it seems. And so as the activation energy is quite high here, a catalyst is added. So sometimes a catalyst can create a secondary, a catalyst can create a new set of steps for the reaction to take. That is its purpose. Its purpose is like, this reaction step takes too much energy, it's never going to be able to occur. A catalyst can be added to alter the pathway that the reaction takes. So altering the pathway could just be like, hey, I'm going to use this catalyst, the activation energy lowers for this step, and so you would indicate that by showing the same blue curve, but on a lower activation energy overall, ending the same, starting the same. That means the catalyst doesn't overall impact the reactants or products, it just offers an alternate pathway. Another way to indicate that is that it changes the molecularity, it changes the number of elementary steps that the reaction mechanism takes itself, so you can see this now has 2 steps here. So the pathway can be altered in many ways, but that's what I mean, is the mechanism pathway is altered, which attains a lower activation energy or a lower energy barrier. So that's another term for it, energy barrier. Catalysts can come in 3 different versions. This is in your reading, and so I'm going to leave some of the reading to you. But the first one is one that's homogeneous, so homogeneous phase. So catalyst comes in 3 versions. You're going to write down just the 3 versions. That might be good. Homogeneous means the same phase, right? And so one of the catalyst examples we just saw was chlorofluorocarbons, which was a chlorine. The chlorine, and this was in one of your examples, the chlorine can be an atom in the gaseous phase, and it affects the ozone, which would be another gaseous phase. So gas, 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 homogeneous. So the catalyst is just in the same phase that the reaction itself is in. Heterogeneous is like catalytic converter. So do I have that example? No. So a catalytic converter in your car has palladium in it. Palladium is a very expensive metal, but it's also a very good catalyst. Palladium, lead, gold, those are very common catalysts in like reactions for in terms of the chemical labs. The guy I worked with over the summer at UNCC, he has so much platinum palladium in his lab. It's worth so much money, but they have to polish it a lot to make them serve as a really good catalyst because it has to have really good contact with the outside environment that they're doing their reactions with. And so I thought that was kind of cool because I actually got to see that. But your catalytic converter uses it, but it's two different phases, right? A solid and then like gases or liquids, which is hetero, right? Two different phases of matter that we're dealing with. And then the last one is the one that you're actually very familiar with, I think, from biology. You have enzymes that serve as catalyst in your body, and so the enzymes have specific shapes. They match the active site of our proteins or other. I'm sorry, the enzymes active sites match the shape of our proteins, carbohydrates, other things that it's trying to react in your body. So we can take a big polysaccharide. Poly means many. Break it down into monosaccharides, which are single sugars. And so it's going to take some time to do that. And so if we don't have catalyst in our body, we would die because we would never have glucose to our brain, right? We would never have anything to tell our body, like, here's your energy, go do what you got to do. So we do have enzyme substrate binding, which is a good example of a biological catalyst. So those might be some good examples to write down. They like to throw out real examples like in your AP exam and so forth. All right, so let's look at the mechanisms that you guys just did. Pulling up the actual, here we go. So in terms of 6, were you guys okay on drawing that step-by-step process in F? Okay. So which was the slow step? The last one. So the slow step literally is the slowest step in the reaction, is the one that's holding up the rate. The rate gets really long because the time it gets really long, the rate gets really slow. The first step doesn't take much energy. The second step doesn't take much energy. The third step takes a lot of energy, activation energy, meaning it's the slowest step. And then overall, this reaction was exothermic. Did it tell that to you? It had to. It said delta H someplace. Okay, so you have to use that as well. Drawing the reactants high, the products slow, so overall the exothermic nature is represented by the graph as well. And I've even drawn my delta H between my reactants and my final products to be negative. You will have a question like this on your exam for this particular test, because they like to make you draw your own graphs. Okay, and label them appropriately with potential energy and then either time or reaction coordinate on the bottom. So put a star by that if anything. What was it? 10 was another one I was going to go over. A little sloppy here. Let me make sure you guys can actually see this. Ooh. Okay, so activation energy was 253. So labeling your axes or labeling your graph with the values is important as well. From reactants to the tippy top, what's the top called? Activated complex or the transition state. There's two different versions of that. It has to be labeled at 253 kilojoules, and then it says the activated complex, activation energy using the catalyst is 118. So that the new activated complex, it's 118 kilojoules, and then overall this was an endothermic process, but it didn't tell us. I don't think it told us the value. Okay, and going down to 12. 12 had another curve system. So I'm going over this specifically because I know that you will have to draw this. Who got down here? Okay. So I noticed that the first step was the rate determining step, meaning the slow step. The slow step initially has the highest activation energy, so it has to have the highest peak, or at least the longest activation energy from beginning to the activated complex. And then, so that's the step I chose to catalyze because it's the only one that really needs to be catalyzed. Everything else should have a somewhat smaller activation energy. Now your graph can look different, but the key point should still be you catalyze your first activation energy because that's the slow step. You've labeled your AB, RA, QB, and so forth, right? So I label my reactants here, and then my first product on the top, and then my new reactants, which is the second step on the bottom, and then my product on top, and then my next reactants on the bottom, and then my product on top. So you can definitely see how that's got a pattern, so it's easily read. And then overall, it's an endothermic process, so from beginning to end, it should be positive delta H. And then labeling, which is catalyzed by showing a dash line or a dotted line or a different color line, is important for labeling your graph for full credit. Questions there? Okay, and the last one is 13. That's what I'm going to go over for now. So I might have to read this question again.
Will someone read 13 for me in my packets elsewhere? Sean, read 13 for me.
Which decomposes to HCl and then the auxiliary temperatures, heat left and catalyst is added. The speed of reaction changes with a minimal amount of heat. Does this mean that the catalyzed reaction has a greater delta H than the non-catalyzed?
Okay, the answer is no. Kinetics has nothing to do with thermochemistry, mostly. Nothing to do with thermochemistry. So catalyzing something, does it change the delta H, meaning the start and end of the enthalpy of reaction? Does it? No. Do not get that wrong in your test. I guarantee that is on your test. It is in the same set of questions where you have to draw your graph. You cannot get that wrong because it doesn't change the start and end. It only changes the path in between. The pathway is how the catalyst is going to be impacting the rate of reaction. So why is the heat, or why does it feel like it's increasing the heat? Well, it's just making a lot more heat really fast. So, sorry, it's making its own heat faster. So it seems as if the temperature is rising very quickly, which it probably is, but it's still going to peak at the same temperature that it did initially. So no, the delta H doesn't change. Most likely reaction is putting out heat, the normal amount of heat, versus at the slower rate, it is not as noticeable. It's not as, you don't measure it as quickly, so it's less noticeable. But as it's made at a faster rate, the heat develops much faster. So that's that number 13. I knew that you might want to have a question for it. All right, let me switch modes now. So I'm not going to teach you anything else today. You've got mechanisms pretty well in your belt. I have one more example for tomorrow. It deals with fast equilibrium, so I know that you're going to mark that later. Go ahead and turn your packet to the multiple choice. There's 31 questions. I think like 2 pages back. Come back one more. One more. I'm going to keep telling you to keep turning pages. One more. Okay, I don't have a page number on this. There are 31 questions. I want you to use the rest of your class time, so you have 20 minutes to get through at least 20 questions. Okay? And I'll tell you your homework is it's reading. But I'm going to ask that this gets mostly done tonight because I'd like to go checking tomorrow. I'm not going to use it as a quiz grade because multiple choice is good for practice right now. You need to practice multiple choice because multiple choice is going to screw up. Okay? So take some time right now, practice that now. If you want to work with somebody, you can. I prefer you work by yourself so that the feedback is more valuable to you versus
To someone else who maybe did the question.
so work now for me.
Hey, Emma.
You can drip that out. I'll make another copy. I'm gonna look in my book bag too. I'll put my Lindsay Sterling back on for you.
That's it. It's not Lindsay Sterling. It's a commercial.